Okay, good morning. Let us resume back. So we'll discuss the evolution of convolutional networks and then GANs and a few applications of convolutional neural networks. So stop me if some things are not clear or if you want to ask a question. Otherwise, I will give a pass after some time.
After the session.
So we have seen how a convolutional neural networks lens. We also have seen how is it different from a neural network in terms of extracting features in its own dimension, in the dimension of data, and how it learns the kernels and the filters appropriate for a particular application. Given that what it needs is a lot of data to learn. One of the limitation of convolutional networks is, if you want, since anyway it has
I just only have breakfast.
it learns in its own two dimensions or higher dimensions. It has so many neurons in each layer, and the number of neurons, and if you increase the number of layers to say 10, 100, okay, and so on, the complexity of convolutional networks is in terms of millions, in terms of the number of weights to be learned are in millions. Okay, the number of parameters or the number of computations are also in millions and so on. Since it needs to learn millions of parameters, it needs, okay, data samples, okay, also of that order. In fact, rule of thumb is roughly we need, okay, 10 times the number of learning parameters, learnable parameters. So if we need 10 power 6 learnable parameters, if we have 10 power 6 learning parameters, we need to have even more number of samples. And in fact, the complexity also increases, again, exponentially with the dimensions. So given all that, the challenge is how to come up with, say, good architectures that will learn across better features. Okay, and if you want to increase the number of layers to 10 to 50, 100 and so on, what are the limitations? And if you want to do that and learn, after developing even a bigger neural network, if you want to learn, how do we get the data sets? Okay, already having the training samples, that means the samples and their corresponding labels, all these are the challenges. Of course, the domain has shifted. Of course, those earlier researchers of this domain are the researchers of this domain emphasize that it needs a lot of data, and they started from around 1997 collecting good data, okay, in terms of for image classification problem, and by 2010, in fact I think 2000 they started, from 2000 to 2010 they have collected millions of data samples for classification, image classification. So they posed it as a challenge in 2010 as image red challenge with 1,000 number of classes. Say they can be cats, okay, dogs, and among cats different classification of cats, okay, and then different objects and so on. So it is 1,000 class classification with, in fact, they have collected 14 million samples and 1.5 million samples they released for the developing for the challenge. And the challenge is to perform better for 1,000 class classification or 1.5 million images. And the initial developments are in the initial phase. The methods are kind of a conventional methods wherein they extracted features from the computer vision. Okay, like histogram of orientation gradients are better features of that sort. And then they applied classification algorithms like neural networks. Since at that time the architectures can't be deep, or in the sense that you can't have hundreds of layers, okay, they are referred to as shallow architectures. And feed-forward neural networks. Also, with that, the errors are on that big data sets are around 28%. So the error is 28%, accuracy is 70% close. And subsequently, they improved with the conventional method. But in 2012, the first convolutional neural network-based architecture, which is 12 layers with reasonably deep at that time, deep architecture, and the number of parameters there are also in millions. So computations are millions. So it requires parallel processing with the 2 GPUs. Okay, they have done parallel processing to in fact 2 different machines. They parallelly process some to some extent and then combine the information. And within that also like each system also does parallel processing, and they divided the problem itself into 2 parts and then they simulated information later. So with all that they could get an accuracy of yeah.
Your screen is
Not showing?
not shared.
Oh. Yeah. Am I there in meeting? Yeah. Thank you. Yeah, request online participants also to speak out in case if it is not. Yeah, sure. Is it visible now? Is it shared and visible? Yes. Okay. So this is the first convolution neural architecture which has taken a leap in terms of accuracy. 10% improvement on that big data set is not easy at all. And this is the first like architecture which has attracted or taken away most of the attention of computer vision and different communities. Okay, in development of convolutional neural networks. And subsequently, people started say this is 8-layer architecture, and the initial stages. Say as we have seen, CNN has convolution layer, sampling layer, convolution layer, sampling layer, right? So the initial developments are focused on how effectively can we learn without increasing too much on the architecture. Can I change the kernel dimension? Say initially they started with 7x7 kernels, 5x5 kernels, and so on. Okay, so if I change, should the kernel dimension be 5x5 or 11x11? In fact, they started with 13x11, 13, 11x11 kernels. So should the kernel dimension be bigger or smaller? Okay, should the kernels, should we have different kernel dimensions also at different layers? And then what kind of, from layer to layer, what kind of activation functions? Okay, what kind of other operations has to be done? Okay, all such things were the initial investigations. Okay, so essentially in 2012 to 2014, the major developments are in terms of reorganizing the information. So if so if we assume that we have a input, okay, so let it be of just some dimension 100 cross 100. Okay, and then assume that we have 6 sets of maps. Okay, let's put probably 3 sets of maps. Okay, so this is extracted. So initially we assume that we fix the kernel dimension. So to extract it, we have actually 11 cross 7. The question is, should we have 11 cross 7 or 5 cross 5 or 3 cross 3? Some such parameter finding. Second thing is, should we have, say from that this is 11 cross 7, if we have, should it be smaller? Okay, 7 cross 7 or bigger or whatever. Okay, so from layer to layer, should we have any difference? And then the subsequent discussion is, see when I want to get features, okay, what essentially if I put 11 cross 11 kernel, what is it happening? It is looking at a 11 class 11 region. So this is called receptive field. That means it looks at 11 cross 11 region and puts a value here. Okay. So if I have a smaller kernel, what does it mean? It looks at a smaller region and puts a value there. So essentially, if I have a bigger kernel, I am looking at a bigger neighborhood. If I have a smaller kernel, I am looking at a smaller neighborhood. Okay. So that, how does it affect in terms of accuracies? That's one question. Now the next thing is, if I increase the number of layers, what am I doing? So essentially, if I have one more layer, convolution layer, Okay. Here if I put 7 cross 7 now. Here 7 cross 7 is putting a value. Is happening. I'm looking at through this at this location. Okay, I'm looking at information of 7 cross 7. Okay, but each of this he is looking at a 11 cross 7 here. So the receptive field here will be much bigger. Okay, that means if I take a point here, okay, or a value in the feature map here, okay. So if I see a response here, it is essentially the response collected from, okay, in the input image, a bigger region, much bigger region. Okay, if I keep going across the layers, after say 10 layers and so on, or 20 layers, each pixel here may see the whole image there itself. Okay, so now the question is, so should I see, instead of looking at 11 cross 11 and 7 cross, one time 11 cross 11, another time 7 cross 7, should I look at parallelly 7 cross 7, 11 cross 11, 3 cross 3 and combine the information? Okay, so should I look at the information at multiple resolutions? Okay, in the input image. So those were the that's another question. Okay, then if I keep increasing the number of layers, okay, I will finally be bringing it to one dimension for classification. Okay, and I will be having an error here, and this error has to back propagate across, okay, whatever 50 layers, 100 layers. Will that happen effectively or not? Okay, so increasing the depth, okay, is thought of, but how, to what extent can we increase the depth of this convolution neural networks? To increase the depth at more layers or to increase the depth much higher, what should be the measures taken? Okay, so these are the key points based on which these developments were made, and initial adjustment was done. Of course, from here to here, the other that is thing that is found or useful or identified is often I perform a kind of convolution. Between performing the next convolution, should I reorganize my content or features or information? Say if I see all this information, it assume that it is distributed with some mean and variance. Assume that all this information is with some mean and variance. Now should I modify this to another mean and variance? Okay, mu dash and sigma dash. Okay, and then do the subsequent operations. Okay, the answer is yes. So I can, if I do not do this, what happens is the information from here to here may be from -5 to +5. Assume that. Okay, or -0.5 to +0.5. It may reduce from -0.2 to +0.2 later. Okay, so it goes in an arbitrary scales. But if I want to do the information or learning, it is better to fix the input range. So what people does is they want to make this mu dash equal to some whatever value, but sigma dash they want to put it as 1, for example. All the time I want to reorganize to have a distribution having unit variance. Okay, so that what happens, the values essentially will be ranging from -1 to +1. Okay, so that will make my see if the values are different or if the values are varying much versus values are being small. What is the difference? In a neural network setting, I want to minimize the cost, right? So I am searching for a minimum cost in a range that is quite varying from layer to layer. See, if I set this variation as -1 to 1, actually what I am doing, this set space for me is in some sense restricted by this -1 to 1. If this goes from -10 to +10, the set space is higher. Okay, like that. So these values which I am trying to readjust, this is now referred to as batch normalization. Okay, what it does is this batch normalization limits my set space always to a standard space. Okay, enables us. This is a kind of a regularization. That is what is done in the first development. So the first is say from 2012 to 2013. They also have done some kind of data augmentation. They have found that already noticed that data is important, so they did some data augmentation tricks. Okay, and these are all practices nowadays used for development of neural networks, convolutional neural networks. And these from here, this is VCCNet. This is very widely referred, and this has 19 layers and 16 layer VCC is also available. So what the finding there is, instead of having a single stage 11 class 11 kernels, better to have 3 cross 3 kernel and increase the number of layers. So by that, what are we doing? So in the first stage, we are looking at smaller neighborhood, okay, 5 neighborhood, and then in the second layer, the same thing we look at 5 cross 5 here. Third layer we look at 7 cross 7 here. So what am I doing? I am going from fine to coarse region, okay, in terms of extracting its features. So that will be better. Okay, that's what is identified and then demonstrated in VCCNet. And then they could increase the number of layers to 19. Okay, and parallelly there is a development called GoogleNet. This is also one of the breakthrough. Of course, this is reasonably well known in computer vision, but they have put it in deep learning framework. What that is, instead of extracting features only at one resolution, why can't I do the feature extraction at multiple resolutions? So let us parallelly do. See, if I want to do a information here, if I have feature map here, let's do say 7 cross 7 convolution. That is extract bigger neighborhood information, features through bigger neighborhood, and then 5 cross 5, 3 cross 3. So extract at different resolutions and then combine them, that information. Okay. So, but to match the dimensions, I may apply zero padding or whatever. Okay. And also perform 1 cross 1 convolution. They have introduced 1 cross 1 convolutions as well. What do we mean by 1 cross 1 convolution? If I have 6 feature maps here, if I want to bring in 12 feature maps, what did we say? We do 6 feature maps, 3D to 2D convolution, okay, to bring a 1 feature map here. Like that, I do 3D to 2D convolutions for 12 times. Okay, that what I am doing, each 3D to 2D convolution is doing one kind of a reorganization of the content. Okay, W1 into this one plus, W2 into this one plus, W3 into this one plus, and so on it is doing here. If I take only one kernel of dimension 1. Okay, so what I am doing, different weighted sums if I do, I will get different feature maps in the next layer. Okay, that is essentially 1 cross 1 convolution. Each 1 cross 1 convolution is a weighted sum of feature maps here. Okay, W into 1 scalar value into this feature map plus scalar value to this feature map plus and so on. Okay, like that with different W's, if I do different feature maps I get. So that's what is essentially used to reduce the dimension. See, if I do keep the information from 3 cross 3 kernels, 5 cross 5, 7 cross 7, all that, what will happen? I accumulate large number of feature maps. But computationally, it is more intense to get the features subsequently. So we want to reduce the number of feature maps simply by applying different combinations. That means here I may have 100 feature maps. I want to limit to 30 feature maps. I combine them nicely with element-wise multiplications, okay, linear combinations, to make only W1 into this one plus W2 into this 2 and so on, one different 30 combinations. Okay, that is what is essentially done in 1 cross 1 convolution. So we can, this is also called bottleneck layer in GoogleNet. So I can, wherever I want, I can bring from 1000 feature maps or wherever, as many number of feature maps, as many I want. Okay, without, it's not computationally intense operation. Okay, with simple linear combinations. Okay, so this is what is done in GoogleNet. They also has made another good contribution in terms of not necessary to say if I want to have a input information here, assume that, okay, and I want to do a output label here. Okay, I need not wait till the last layer to do back propagation. I may have some information here, feature maps. Let us do from here itself concatenation and bring 1 dimension. Okay, give the labels here also, back propagate. So again, give the labels here also, back propagate. Okay, multiple instances you can do at in all intermediate stages, some of the intermediate stages. You can do back propagation to adjust the weights better. Okay, to adjust the kernels better here. Okay, so this is done in GoogleNet, and with that, this is a very computationally efficient architecture at that time, and accurate. It is much more reasonably accurate. It's all on par with VCCNet and defeated VCCNet also in few scenarios. So then the subsequent developments, see, up to GoogleNet in 2014, so they could bring only up to 20 layer architectures. Okay, but the other people envisaged of having hundreds of layers. So what they thought is, see, why should I learn? Okay, from layer to layer. Okay, the whole information that see, here to here I have already learned some information. Okay, but this information is not there here. Okay, can I also have this information here? Or when I want to learn from layer to layer, I want to learn only the information that is not already learned up to here. Okay, so that is essentially is, can we have a stiff connection? Okay, to learn only the complementary information. The idea is this: from already I have learned up to here, this information let it take directly. Okay, and learn only the residual information here. Okay, so these are all called actually resonates. Okay, residual learning mechanisms. Okay, and this is called stiff connection. So essentially what will happen because of this, there are two advantages. One advantage in forward pass, as you can see, already the information learned x is already here. So if I want to learn g of x, which is equal to f of x plus x. Okay, why should I learn g of x? X is already learned. G of x minus x only I will learn. That is f of x only I will learn through convolution. The other advantage is in the backward propagation or back propagation, already there is an error here. The error will come as it is here without any damping factors. See, here I will have all multiplication with the W's. Most of the times W's, weight elements, are in the range 0 to 1 only, or even much smaller. So you will have less contribution of the error. Okay, as I move on, if I over many layers. Okay, but here I whatever delta W I have, delta Y I have here, or delta W I have, delta values I have here. That delta value directly comes, in fact, if I put a skip connection up to here. Okay, I can of course put skip connection up to whatever number of layers. Okay, so that is what is done in Red. So they could demonstrate with 150 layer architecture and in fact 1000 layer architectures as well. So with this, these are very famous and quite used. The other idea is, see, why should we give equal importance to all channels? See, of course, I am learning from one filter, say from one input map, feature map to several feature maps. Okay, through different filters. Okay, each filter has its own advantage. But should I give equal, say from here to here, I'm again learning 6 tools and maps. Okay, so should I give equal importance to all these maps? So I assume that I want to bring in 6 maps to another 6 maps. Okay, with I don't want to change the number of maps, but what I want to do is I want to prioritize these maps, give relative importance, different importance to different maps. How do I do that? Okay, so they come up with an architecture called squeeze and excitation. What essentially is done is assume that I have C feature maps here, 10 feature maps. What I do is, what each of these feature maps represent essentially the salient information of the input. Okay, at that feature map. That means if there is a face here in 20 cross 20 location, in one of the feature maps, surely which will recognize this, which will be helping us to recognize the face, there will be a very high value of the feature map. Okay, that's what happens. Okay, so essentially what these feature maps are representations of the features which will highlight the classification layer. Okay, so essentially what is happening here is these feature maps, whichever are having high responses, are more important. Whichever having small, medium responses are not very important. So they have performed a global pooling. Global pooling means global averaging or global pooling. So if I have 100 cross 100 is the dimension, and I have 10 feature maps. Okay, they average all across. They sum across all 100 cross 100. Okay, or average also is fine. Or get a value here. So like that, if they do for 10 channels, okay, they will be getting 10 cross 1 vector. Each value is essentially the sum of all that elements in that feature map. Okay, so like that, I have got a 10 cross 1 vector, right? So this 10 cross 1 vector is essentially what it represents. It represents the global strength of the feature map. Now, I want to weigh each of these feature maps. Instead of directly weighting these feature maps that by corresponding global average value, they have applied a learning mechanism here and feed forward neural network, which will learn from 10 neurons to 10 neurons again. Okay, In between, I may have a layer here, which will learn from 10 neurons to 5 neurons or whatever neurons, and then go back to 10 neurons. So finally, what I'm getting here, through learning, why did they put this? Through learning, when I put, I will decide how much weight also I can give here. I need not rely completely on this average value here. Okay? So after learning, if say this one gets a very high weight, it means that this feature map gets multiplied by that weight. Okay, correspondingly, each of them they multiply. The squeeze is, so they are putting large details into, say, they are putting into 10 cross 1 vector. 10 cross 1 vector 2, they will put 5 cross 1 or 2 cross 1 and so on. And then put 5 cross 1. Okay, put to 10 cross 1. And then bring to the original dimension. Okay, 1 cross 3 and multiply element wise. Okay, element wise means first map into W1, second map into W2. They don't sum here. Okay, like unlike in 1 cross 1 convolution. 1 cross 1 convolution, you put the W1 into a whole map plus W2 into whole map. That is 1 cross 1. Okay, fine. So this is essentially is done. This is referred as squeeze and excitation. This is a kind of a first attention mechanism in convolution networks, essentially in terms of channels. Okay, so how do we bring in attention in channels? See, once the base architectures are developed, the interest is on where should we focus on. So essentially a kind of an attention mechanism. Attention can be done across channels, okay, across regions. Okay, that means some regions may be more interesting, or across say essentially taking which layer. That means let's develop a kind of a up to some layers you learn in some fashion. Get a summary of attention there. Okay, use that to weigh subsequent development. Okay, that means what they do is if I learn up here, I may have a feature map. Okay, in this feature map, I may bring in a simulated feature map from this. That means I may perform 1 cross 1 convolutions to bring in one heat map. Okay, one feature map. That means if I have 10 feature maps here, if I perform 1 cross 1 convolution, just a 2D convolution, and learn, I can get only one feature map here. This itself can be considered or learned as a heat map. That means attention map to guide the subsequent level. Okay, so essentially it can be done at the layer level or at the channel level or at the spatial level. So the subsequent developments has done all this. These are the main developments in convolutional networks for classification. Of course, there is one more, that is why other architecture that is also well known, that is dense net. What these people have done is, these also wanted to do skip connections, but the idea is not to bring learn only the information that is not there from layer to layer, but bring the whole channels itself. That means what they do is, see here, assume that we have 6 channels, here we have 12 channels. Okay, if I want to learn from this channel to this channel, they bring concatenate all these 6 channels also with this 12 channel. So essentially the number of channels will increase from here, say 6, assume that here also 6, 6 plus 6, 12 it becomes, next 12 plus 6, okay, it will become 18, and 18 plus 6, it will become 24, like that. They are not concatenating, they are not only taking the input information or through after some layers skip connection. At each channel, they are concatenating the channel information itself. Okay, and then they learn up to that, say after some time what will happen, the number of channels will become very large. Okay, then what do? They want to reduce the channels. So if you want to reduce the channels, what is the mechanism? If you want to reduce the channels, what is the mechanism? Apply 1 cross 1 convolution. Okay, that's all. Bottle like layer, that is called apply 1 cross 1. They apply 1 cross 1 convolution. Okay, that's all. And then go again with another dense block. So this also is a celebrated architecture. By 2017, these are all different variations of the architectures, especially for the classification problem has come. And these are the key networks are the key developments that are used in other computer vision applications as well for convolutional networks developments. Of course, after that, the challenges, there are other challenges which became more famous than ImageNet, because it reached almost a saturation accuracy of 98%, 99%, and so on. So even on that big data set. So there are other data sets that are required for each of the application. So then the interest has gone to acquire the good data sets and then develop architectures for other computer vision methods. Also, many of the references are from the Stanford web page. So Professor Fifi Lee and their team have given nice video lectures. MIT, so the Stanford team has nice video lectures. So they have given good pointers to data sets, projects, and so on. You can also do that. So now what I will do is, if you have any quick questions on convolutional networks for classification, you can ask. Give a small pass. If you don't have any question, we will move on to other computer vision. Yeah, you can ask any question. There are some questions here.
Yes, sir. They will. In the chat box.
Some questions?
They were like from the last session.
From the last session. Okay, we'll take chat box to do that. So those who want to ask can ask. Otherwise, we will discuss at the end. Okay, well, let's move on. So then the interest is not just on classification. For inference from the scene, we need to detect objects. We need to segment the regions of objects. And we want to understand the whole scene as well, composed of objects. So how do we do that efficiently? So these are all the different tasks of some of the different tasks of computer vision. So this is called the semantic segmentation, wherein we want to label each pixel. That means, say for example, here is cat. If I have 100 cross 100 image, each pixel I want to tell whether it is a grass, okay, or a sky, or a cat, or a tree, and so on. Okay, that is semantic segmentation. Okay, and this is object detection. I want to detect each object. Okay, so whether where is the cat, localize the object. Detect and localize the object. That means I want to say that here is a cat or a dog. Okay, and then dog exactly is at 10 cross 10 to, okay, some which is the location where it is there. So we want to give XY where it starts, height and width. Okay, so we want to give XY HW. Now those dimensions of the bounding box. And we want to give a class label. Say that whether it is a cat or a dog or whatever, other object. Okay, this is called instance segmentation. If I get, I think, 3 dogs here. Okay, so we get actually 3. So how many dogs and how many cats? I want to distinguish each. If there are 10 persons, each person has to be separately labeled. Okay, separate, re-identified. Okay, each instance is different, even though they belong to same class. That is instance segmentation. So these are some typical problems in addition to tracking and a few other problems that we have discussed. So now the question is, how do we use this convolutional neural network architecture as we have seen from 2014, 2010 to 2017 and 18. So there is a lot of research and work, many works on developing them for classification, better and better architecture with the aspects that we discussed. Of course, the interest also has parallelly gone into the development of other computer vision tasks as well. And we discussed few of the good architecture, very well-known architectures in this, for other tasks. Say, for example, if I want to consider semantic segmentation problem, that means we want to label each object in this scene. Okay, now how can we use a classification model for doing it? Assume that if we have a network developed for classification, directly if I want to use it here, okay, how do we use it? We take each patch, okay. Class classification means grass or cow or whatever, grass, cow or sky or whatever. Okay, right? So each patch we give a label and that label we put at the center. Okay, Like that, if we do for each patch, I get a label, and the labels will also be of dimension of the image. For 100 cross 100 means labels also will be 100 cross 100, right? That's what I want to achieve. But it is very computational intensive because I am applying CNN, okay, for several times. If it is 100 cross 100 image, okay, 100 cross 100 CNNs I am developing. It is too much, right? So the architectures have come up saying that why don't we learn all together? Okay, that means let's not get into the one dimension at all. Directly do it in 2 dimensions. Anyway, we need finally the labels also in 2 dimensions. So then we start with 100 cross 100. Okay, somehow we make the feature maps at the subsequent layer as well 100 cross 100 with some zero padding or whatever. Okay, and then we can learn directly from here to labels. So the cost or loss functions now will be in 2-dimensional here. That means at each pixel I have a loss value. And aggregated loss is what I want to backpropagate. Okay. So now, but the challenge is this is at each layer having 100 cross 100 feature maps and having more feature maps and more layers will be computationally intensive. Then the idea is, can't we reduce in between? Let's be in 2-dimension, but still let us reduce in between. Okay, the dimensions of the feature maps. Of course, you can increase the number of feature maps. Okay, but and then let's resume back to original dimension. So what am I doing here? I am doing downsampling and subsampling and pooling here. Okay, and to increase the dimension, I may do a kind of unpooling or I may do a kind of upsampling. Okay, same operation like we do in backpropagation essentially is done here. Okay, but this is in the same architecture. Okay, so this is called encoder, which will encode the image information into features, and this is a kind of a decoder. Of course, it's decoding in terms of labels here. Okay, so and if I want to get back the original image itself, there are some architectures which I will discuss later. Okay, which will try to get the original image information itself back. Those are called autoencoders. Okay, so essentially what here we want to do is we want to do a kind of a feature extraction, encoding, and then decode into the labels. So there are different ways in which we can increase the dimensions. Okay, unpooling. So I will skip the details, but these are essentially in the similar lines that we have discussed for backpropagation. Okay, where if we are averaging, we put the value for 4 times. Okay, there is one different way of doing upsampling in terms of the or in decoding, that is done through transpose convolution. We do convolution in forward pass, right? So here to reduce the dimension, we are doing convolution, or while reducing the dimensions, we are doing convolution. Transpose convolution is essentially multiplying the same kernel, okay, with each of these feature values, okay, and then adding with substrate. So I skip why the name transpose convolution comes. It's essentially those who know convolution matrix form. We are doing a transpose of it and doing the convolution. So with this, several architectures have been developed for segmentation. Some of the key ideas that are used is like in computer vision, why can't we analyze the information at multiple resolutions? Why should I do only at 100 cross 100? Okay, if I want to do segmentation here, okay, so why can't I reduce it feature map dimensions to say 1/4 of dimension? Okay, 1/8, downsam, 1/16, 1/32. And at different dimensions, let us learn parallelly feature maps. Okay, and then at each dimension, either you can directly backpropagate by downsampling the labels as well, or you can do a learning at each dimension and upsample, okay, the information and then fuse the information and then backpropagate. Okay, the idea is if I see the image, same image, whichever I say, if there are some aeroplanes going and there is a soldier, I want to capture both the aeroplane and the soldier. If I look at 100 cross 100, soldier will be seen much better. Even aeroplane can also be seen. But the soldier whole information may not be very well seen in a single feature. So are effectively encoded. So what we do is at bigger dimension, when we see at bigger dimension, small objects can be seen better. But when we reduce the dimension, okay, it is computationally efficient and compact representation of the objects happen, bigger objects will happen. So both information we take together. That is referred to as multi-resolution analysis. Those who know a little bit about wavelets and so on, essentially the idea is there also is similar. in terms of extracting information at multiple resolutions. And they use this in the architecture itself here. So there are several developments has happened. Of course, SIGINT unit, the attention unit, and several other unit variants are well known for segmentation. Similarly, DeepLab has a good library for segmentation. Mask RCNN is also a good approach, and YOLO VA now does detection and segmentation. RefineNet, HRNet, these are all few developments. Pixel to pixel GAN and so on. So these are very celebrated applications are autonomous driving applications for segmentation, and also satellite image segmentation and so on. This is another area where people have spent a lot of like efforts and then developed methods, and very widely applied in or needed in computer vision. Detecting the objects. Of course, segmentation is conventionally is very difficult. The advantage of deep learning has made, or the development of deep learning has made segmentation reasonably much simpler, I would say, because conventional way of segmenting an object is very, very difficult. So object detection is also of one part of that. Of course, as not as difficult as segmentation, but reasonably difficult in computer vision, and can be addressed comfortably or conveniently in deep learning. Also, here also there is a quantum jump in terms of the accuracies after deep learning based methods, and there are several architectures that has come up for object detection. We will discuss the object detection, how it is done now. So essentially, if I want to detect an object, the question here is, I want to say where is the bounding box region of interest of the object. I want to tell what the class of the object. So essentially, I want to learn the bounding box coordinates, that is x, y, x, w. Okay, and I also want to give a label. So essentially, x, y, x, w are the real numbers. If I want to learn the real numbers, the process is regression. And if I want to do a classification label, the process is classification. So I want to do both of them together for object detection, right? So for segmentation, no need of regression, because at each pixel I want to give a label. Okay. So essentially there it is only label learning, but here I want to do the coordinates also, localize the object. So here this is posed as regression, this is posed as classification, both are done together in object detection. That means I want to detect the object, means I want to learn the coordinates and as well as the classification label. Now the question comes, see where the object is not known, so I can anyway do like a conventional CNN. Okay, and then get full features and then learn both of them together. The beauty of this the convolution neural networks is I can initially start with, say, even the bounding box coordinates can also be adjusted. Okay, I can say that which location the object is there can also be adjusted from the features, because these are essentially global features, but still they will help us to learn the local locations. But the question is, if I have multiple objects, I don't know a priori, like exactly in say NLP or in say RNN. So where we don't know the number of words, number of letters, and so on. Okay, in prediction task. So similarly here also we don't have the number of objects. And then how do we learn it? So essentially what need to be done is we have to search across each of the image patches, across each of the skills, and essentially want to identify the number of objects. Okay, so initially the thought is to have multiple bounding boxes learning through multiple heads. But later the idea is to use, like in computer vision, can I search overall, okay, and see the regions of interest. Okay, and at the regions of interest, can I identify where, that means region of interest here is exactly the location of object. Okay, I say that here object is there or not there. What object is that is not important at the beginning. Whether object is there or not there. Okay, that way I will try to learn first. That is done in computer vision usually. So region of interest can be found. Once we find the region of interest, we do classification. Okay, there we extract features and do classify. So same thing now, similarly, selective search methods essentially will help us to do it quicker or faster. Once we get the regions of interest, can I then apply my CNN ability to learn the features and then classify? Okay, this is the initial development. After that, what people thought is, why should we depend upon okay, for the regions of interest, or have an end-to-end approach where of interest can also be learned, okay, and then that means region of interest means object is there or not, and which is the region where object is there. That means x, y is w of the object, and the object is there or not is a binary label. Okay, yes or no answer. So if I take this region, in here object is not there, no answer. Okay, so let's go. No need to see the coordinates. Here object is there. Okay, so I want to find the coordinates, regress the coordinates as well. Okay, so wherever object is there, I have to regress also in sense that way W also. I have to find where objects are not there, no need to find the coordinates. But I have to find for each patch whether object is there or not. So can we do that through learning the features? The idea now is let's get the features first. Okay, and the feature space itself let us set, and then let us have that in this game. Okay, so then here these are called region proposal networks. What this proposes in this region, object is there, yes or no. Okay, and gives the XYSW of objects. Okay, there. And after that, let us put as a second stage of learning, okay, which is from the regions of interest. Can I tell what those objects are? Fine tune the XYSWs. That means previously I have got a coarse region of object. Okay, I want to localize it precisely or finely, and also I want to get subsequently better which class that object belongs to. So essentially what I'm doing here is region of interest. I am finding here, I am saying here object is there, object is not there. That's all. Yeah. Okay, this is region proposal network. And from here to here is a kind of a these are called RCNN, region convolution networks, and faster RCNN and fast RCNN. These are the developments on the same lines. Okay, so fast RCNN does actually from here to here whole end-to-end learning. Whole features are learned first, some features are learned up to some scale. After that, identifying whether object is there or not there, and then we are identifying which object it is. Okay, so that's essentially is done in a two-stage approach. This is essentially the cost function, where there is a classification loss and a regression loss. Wherever there is an object probability, then only this regression loss works. If there is no object, no need of regression loss. Okay, so like that it happens. And this is done in a stage manner. And they also have a idea of using anchors. Anchor means, as we discussed before, if I want to identify object information better, I have to search across different scales or different resolutions. I can't say that at one resolution I may not be able to get all the objects. So what people does is one way of you resample the image itself, 100 cross 100, 50 cross 50, 25 cross 50. Or you change the kernel dimension like we are doing here. 11 cross 11, 7 cross 7, it looks at different scale. Or what these people have done is, see, if you identify a rough region of object, that region which you are considering, okay, that means at that location you put different size kernel. That means this object now may be of bigger object or smaller object, I don't know. So what I do is I will scale that, say I will compare it. Okay, this one with bigger scale one, that means different aspect ratios as well. Okay, that means object may be like this, object may be like this, and so on. So initially I localize roughly and then identify with which anchor will it suit well. Okay, for that. So that is done usually in all networks, no object detection networks. So the later developments are, why should we go for two-stage approach? Why can't we why should we first learn regions of interest separately and then go for a learning of object classification? Can't we do together? Okay, those are the one-stage object detectors. They are called. YOLO is one good example of it. Another parallel line of thought is, can we do object detection and segmentation together? Okay, mask RCNN is a architecture which does that. What we want to do is, after anyway we are localizing. Okay, in that region, let us get for each pixel one label, whether object is there or a person large background is there or whatever. So get a segmentation mask as well. Learn the segmentation mask as well. Get the region of interest. There itself you learn one segmentation mask and you better fine tune the XYSWs. Both learn together. Okay, learn the XYSW region of interest. Okay, region mask. So this is mask RCNN. So this is also very well known and widely used in computer vision. Then, of course, in parallelly in object detection also, people have got an interest to check. In computer vision, there are two parallel line of development. One is feature-based methods, other is dense methods. Feature-based method means, like I mentioned, they look at only key points. They doesn't look everywhere. Okay, and then from that they want to make inference. And in dense methods means whole image, like whatever we have seen so far are dense methods. Okay, kind of dense methods. Then people started corner net, for example, or center net and so on. They wanted to see if I take only key points. Okay, can I learn the key point itself? And if I want to just represent with 5 key points or 4 key points. Similarly, like person with 20 landmark points, face with some 100 landmark points or whatever. So can I learn landmark points and then make a better inference from that? Okay, so they also found good. So they used that also parallelly. People wanted to understand which pose, okay, a person is doing in a video, for example. Okay, then also these key points work well or help well, because based on the location of key point, they will tell whether a person is standing, sitting, or whatever he is doing and so on. Okay, because you know exactly which key point location where it is. From that key points, you can tell many other inferences. So this Mask-Gaussian is one of the very good architecture which has all these in place. So as I mentioned, YOLO directly tries to do, so at each region, they will try to get the anchor boxes and try to see whether is it a region of interest and then what region does it belong to, what class does it belong to. Also, they learn all parallelly, okay, in class level and then as well as the X, Y, Ws and so on. Also, in YOLO developments, there are several YOLOs. YOLO V8, V9 also might have come. So they each has enhanced version of other in some sense. So there are transformer-based transformers are the recent trend in terms of learning methods. So they do learn very good features. Of course, their abilities in terms of bringing better attention. So they bring the information in terms of different chunks of information, and then try to see where the similarity is self-similarity or the cross-similarity is high or low. Based on that, they try to learn. So essentially, in that way, they do well even for image computer vision domain. So they bring in very good attention mechanism. Of course, they are very computationally intensive and takes weeks or we don't have good GPUs, months to learn. But there are developments. Each of these methods, transformer-based methods are there in each of these areas. DETR is one of the methods for object detection. And visual tracking is another area, as we discussed. It tries to find out the object track across different frames. Of course, there are several initial developments for visual tracking are based on correlation. And doing this correlation, that means if I have a template, if I want to find out the same template in a frame 1, frame 2, frame 3, in each frame I want to do correlation. But the advantage in visual tracking is we already found a template in the frame 1, means the same object I want to find in frame 2. It might have moved only in the vicinity, right? It doesn't go somewhere else completely. So we search only in a smaller set region compared to object detection. The main difference between tracking and detection is tracking does only searching in a small region. Detection does search in a much bigger region, in a whole image. Okay, that is the difference. And tracking methods now comes with tracking by detection, tracking and detection and so on, which want to search whole across as well, because some person has moved like this and again gone out and entered from there. Okay, so you can't keep searching this side. Okay, you have to see whole image. So like that. So detection is also plays a role in tracking, but tracking methods essentially look at in the vicinity. And initially, as I mentioned, correlation-based trackers are very well known. Subsequently, they wanted to do correlation better in frequency domain. Okay, so they reduce the computation. Those are called kernelized correlation filters. Those who know a little bit of support vector machine, okay, they applied a trick of kernel trick here again, and they did it in the frequency domain, bringing some matrix operation of correlation into element-wide operations in frequency domain, and did it much more efficiently, almost much more real time, more than real time, fast. And similarly, there are several developments, efficient correlation operator and so on. And in deep learning, the very famous tracker is the Chinese network and the class of Chinese network trackers. The idea is very simple, almost similar lines. You have anyway image here or search region here, you have a template here. Extract CNN based features, you apply some kind of convolution layers here, okay, and cooling layers. You extract same set of convolution and cooling layers here. You have the information, okay, of features in feature space, correlate in feature space, which is at much lower dimension, okay, than the original, and much efficient representation than the original. Okay, and do it a correlation here and see the response map and use the location of the object. That's all. Okay, so instead of correlating the image space, extract these features and correlate in the feature space. Okay, and essentially the other thing that which I have not discussed or which I am not focusing is on the loss functions. Which loss functions are better for what operation? Okay, so there are plenty of course, loss entropy is very well known loss function that is widely used. In fact, first to use. Okay, and then there are other loss functions. Mean square error is also widely used and well known. And there are many other loss functions. Okay, in each of these areas, how do we develop a loss function, especially when we want to learn with lesser number of samples? The conventional loss functions doesn't work. Also, when we have actually one class having 100 samples, another class having 5 samples. Okay, it is called imbalanced classification or imbalanced scenario. So in imbalanced scenario, if you want to learn and do something with conventional class functions, it doesn't work. In fact, our group also focuses on developing better loss functions for imbalanced scenarios. So how do we come up with which loss function is better for a particular application? Of course, for different tasks as well, you need slightly different tracking and different loss function. Here for tracking, they use cross entropy only in slightly different flavor. So I will skip the details. Of course, in each of the cases, there will be several challenges. Even though the methods are elegant and we are using large data sets to learn, the real scenarios are even more challenging. So you can always get a challenging scenario where this way. And of course, which I am not discussing, probably some other people will discuss, is on attacks. So even if you train well in neural network, in the exactly, since it is mathematically guided, you can do a reverse mathematical operation. Okay, instead of increasing the loss, you can decreasing the loss, you can increase, and create a scenario where it completely fails. So on adversarial attacks, how does it work? So here is the conclusion for the CNNs apply to computer vision. So probably I will discuss shortly on subsequently on the GANs now. So if you have any quick questions, you can ask.
So,
Yeah, please.
why not use clustering for object detection? Clustering techniques.
Yeah, people use, of course, clustering. Essentially, they use to find out the reasons of interest. Say the essentially apply initially they use clustering only for segmentation. Also, they use the reason of interest can be obtained through clustering. Once we get the reason of interest, you can get the yeah. So clustering also question is what features do you use for clustering? So it's very important to have better features when you want to do clustering and what clustering is kind of. Yeah. It can be used, but it has a much more better edge. Yeah. Okay, any other questions?
In the chat box, sir.
In chat box, sir?
Yes, sir.
Then you can please. Yeah, we will take probably how much time do we have? So, around today, sir. 12:45 p.m. Oh, you requested to set. Okay, fine. So I will take probably some. Okay. which is the pre-trained model, takes less time for training. Okay, fine, good. So it depends upon what application, and for each application, of course, there are now plenty of models. So for so object detection, we can use mobile net kind of models. Of course, even for classification, there are mobile net based models. SSD is for detection again. Single shot learning and so on. So you can for application to application it differs, and for each application there are. Which model is best for detecting the emotions of students? Okay, fine, good. Yeah. So it's essentially we cannot tell like that. So probably I am not very familiar with expression recognition models, but those who are good for classification also suits well. Usual idea is nowadays they want to have a skip connection in the model, and they want to have reasonably different architecture if you want to have more accuracy, and you are not limited by the real-time requirement. And also kind of for segmentation kind of things, encoder decoder has to have the information that is through skip connection. That means the information that is there in encoder is also passed on to the decoder. So these are the general rules, but it depends upon the application. Position encoding have been effective in VITs. Okay, what is your opinion whether they will work on MLPs? Okay, since one of the disadvantages MLP over CNN is that they don't encode locally or inductive bias towards neighborhood pixels. Are there weight initialization techniques to have CNNs like behavior like? So essentially, weight initialization is very well explored even in CNNs. There are several weight initialization methods suggested. Of course, Xavier based approach, that is the very well known thing is if you have the range number of neurons in neural network in MLP, if you have the number of neurons in the output layer, based on that in the next layer, based on that we put -1 by root d to 1 by root d. That means you want to say that, say, of course, the d is the dimension where you are, and if you want to go for the next layer and weight in this list, you want to do there. So -1 by root d to 1 by root d is the range. They want to put the weights in such a way that the output is in the -1 to 1 range. That is the idea. So like that they put the initialization, they restrict the initialization. Because you will be adding all these elements, W1 x1 plus W2 x2 and so on, it has to be much lesser than 1. Okay, the weight has to be much lesser than 1. So that is for NLP. Similarly, also done for CNNs. So they calculate fan in and fan out. It depends upon the number of channels and kernel dimensions. Based on that, they will initialize. So there are some standard procedures for that. Position encoding, I am not very sure whether MLPs will help or, because MLP, the main problem itself is we are getting into full one dimension. So I am not very sure. So well, whether we have to have convolutions in my view we can't get away with complete 2 dimensions and do well. Best classification model for detecting student dropouts. Okay, fine, good. Yeah, that depends upon sequence data and so on. So if you are looking at year to year, then it is different. So probably if you are predicting, it's not detecting, then it is RNN based model and so on. Where is in class imbalance in the data set? Okay, so where are the class in? Okay. I'm not very clear on the question that Shraddha has put in class imbalance. So essentially, most of the data sets, real data sets, has class imbalance. If a question is about where does class imbalance occur in data sets, so for example, COVID data set. If we see, we have hundreds of thousands of COVID samples which are available. Okay, versus the lakhs of pneumonia, lakhs of normal chest X-rays. If we see chest X-ray data set, we have lakhs of chest X-ray samples, and we have at the beginning we only have hundreds of chest X-rays with the whole. So there is a great imbalance. Similarly, now even in object detection, the problem is rare object detection. So which occurs very not frequently. Now and then objects occur. Say drones, for example. So how do we detect them? So some such problems are important. So all these scenarios has data imbalance. That's the computational complexity depends upon the number of layers. Yes, surely it depends. So it depends upon the number of layers. It depends upon the channels. It depends upon the dimension and all this. Would you please make a PPT available? Okay, so that's fine. Thank you. We'll do that. VCC features extractor used extensively, even more than ResNet. Okay, are they any specific features that make them more protein? So essentially, it's not that VCC features are used more than ResNet and so on. VCC is compared to the ResNet, full ResNet models and so on, VCC is lightweight. And VCC is one of the very well-known and initially developed model. So people at the first stage use VCC. It's not that. In fact, ResNet 18-based model you can make much more with our ResNet models you can make much more efficient with that. With skip connections you can design, or with all the techniques that are available now, we can design even lightweight architecture, much lightweight architectures. Then even in object detection, UNet is very well-known model, but compared to UNet, very lightweight models are there. So most of the models, if you want to find the lightweight models, light will be there in lightweight models. So it's another question I have is the features extracted. Okay. So what is the criteria to set the dropouts in VCC? Usually they put 0.5 as the dropout probabilities, but you can have it also higher dropout or lesser dropout. Dropout is essentially, so I assume that I designed a big architecture, but I don't want to rely on all the, there is not, all will not contribute equally. So I want to have only some of the active parts. I don't want to have all to be active. So I know that roughly 20% of these will be active. So I put dropout probability as 0.2. So like that. So I want to remaining all connections are done. So of course dropouts are widely used, but it's also a regularization trick. Each time we change the dropout, say randomly we sample. Like say if I make dropout can also be done across layers, across channels and so on. Also if I drop out across channels, I'm out of 6 channels, I'm selecting 2, assume that, or 3 I'm selecting with 0.5 dropout. Then each time I randomly select. So what I'm doing, each time I'm doing a slightly different regularization. It's a kind of a different optimization, different regularization. Could you please share? Yeah, sure. Yeah. Any other questions? Fine. So now let's resume move on to the discussion.
Meanwhile, sir, just give us couple of minutes, sir.
Yeah, sure.
Thank you very much, sir. Your nice lecture. You planted seeds of research in so many researchers. One of such a student inspired from you, still continue. You want to illustrate with you. Dr. Chandrasekhar Samsung R&D want to illustrate with you, sir. Give us please, sir.
So Chandrasekhar is known to me well. So yeah. So he, of course, it's out of the dark. He is from Sri City, so he used to approach during his PhD days and work closely. So to make some good contributions for him and for me as well. So he is very active in terms of bringing so many contributions. Currently, I think in that.
Thank you very much.
So we have a 10-minute break, right?
You want to take break now? We will take break. Yeah, already one but it's not more.
Do you want one more break? No. Okay,
Yeah,
sir, you
after
can
that.
continue.
So we'll resume back for the discussion on generative adversarial networks. So hope it is in full screen mode and you're able to see this slide. Yes, right. Okay. The other, in fact, one of the after CNNs, so they have influenced a lot, and people have spent years on developing them better. And in fact, they could do, in fact, wonders which can't be done in computer vision or many other fields. In fact, even in speech processing and many other fields of conventional signal processing and AI in general, they were able to do. So, in fact, in terms of computer vision, it is started in 1960s, and 1960s to 2010, 50 years, okay, which can't be done or which was done, okay, in a different ways, addressed in different ways, could be done with a single way of using convolutional networks. Of course, there are also several changes, but still, they could make it much higher in terms of the accuracies and the ability to do. Of course, they do have several limitations, but it was achieved through CNNs. So after CNNs, one of the breakthrough, if you want to tell, it is the GAN, generative adversarial networks. What these GANs are slightly different than CNNs. Of course, the element composition of GAN is through CNN or convolutions and poolings only. And the learning way is also like we do back propagation and so on. But the key difference between CNNs and GANs is the CNN, we say, for example, it's like we are teaching it and it's learning. Okay, like so we are doing a kind of a asking them to learn, and they are supposed to listen to us and directly and learn. Okay, we are not giving a chance for them to explore independently. And in GANs, we don't see the labels. Those who want to essentially learn doesn't see the labels. So we give them a chance, we give a set of questions and ask them to come back. Okay, and see how good they are. Okay, and then tell that these are not good, that these are good in a supervised way here. Now, unlike reinforcement learning, where we give just a feedback of reward or punishment, we give in a supervised learning fashion, but still a feedback on the things that are learned, partially or learned, and want to see that, okay, both this feedback is utilized to learn better. So it's a kind of a critic or a two-player game, people say. So where one tries to kind of a generate whatever is required, and other discriminate whether it is correct or not. Discriminator is almost like a CNN, conventional CNN used for classification. But generator is slightly different. The objective of generator has begun with the two kinds of different class of methods that are there in conventional machine learning. So in conventional machine learning, there are two different kind of methods. One are discriminative, other are generative. Discriminative means those who are quite familiar with probabilities or Bayesian classification. So if I give a label, okay, given that this is the label I want to get. Okay, given that image, what is the label? What is the maximize? How do I maximize the probability of label? Okay, that is discriminative. That means, say I know anyway label. I have given the original image. I want to see the probability of label being maximized. I'm not interested to get the original sample or the distribution of original sample. Say, for example, in phases, okay, if I have 50 different students in a class, I want to classify each of these, recognize the phase samples into 50 categories. Okay, they recognize the phase. I have, say, 10,000 samples of phases. All these 10,000 belongs to 50 categories. And say, assume that there are, in this 10,000, assume that 500 belongs to one category. Okay, another some 400 belongs to other category, like that. Now, my objective here is just I want to tell given any phase from this 10,000 or similar of say phases of these people, I want to tell to which class does it belong. So I'm only interested in given the data, that is X. Okay, which is the highest probability that I can get for y. So P of y I want to maximize, given x. That is my objective. In conventional or in CNNs. Also in discriminative learning. Okay, in discriminative learning, and it is done in CNNs. But generative model, what it tries to do is, see, I have 10,000 samples, fine, and I have 50 students, okay. I want first student, okay, assume that 500 samples I have. From these 500 samples, can I capture how the samples of this person will be? That means this person, can I generate if 500 more samples of this person? Or can I get the distribution of this person itself, the sample distribution of this person? Okay, that's what we want to capture, the distribution of the samples. Okay, if I can capture the distribution of samples, I say that these samples have roughly Gaussian distribution. Okay, if I keep throwing some random number, 0.1 numbers. I say that among these 500 of random numbers are from class 1 or have come from n1 comma 1. That means mean 1 and variance 1. Okay, another 500 or 1000 have come from n2 comma 1. Okay, so can I now tell that given these 500 samples, first 500 samples, rather than telling that it belongs to class 1, that is n1 comma 1, can I capture that they belongs to Gaussian distribution? Also, mean of these samples is 1 and variance is 1. So they are essentially are originated. These all have come from, okay, a Gaussian distribution of n1 comma 1. If I capture it, what am I doing? I have the whole information with me. That means I can generate from this 500 samples any number of samples. Okay, I can sample again Gaussian distribution n1 comma 1. Okay, Gaussian distribution is just defined by mean and variance, right? So I can sample it for as many number of times, I can generate as many number of samples. Like that. Now the question is, if I have 500 samples of his face, some use may not be there in that. Okay, some different scales may not be there in that. Different variations of a person's face may not be there in that. If I capture the distribution, I can generate the many of such which are unseen in the data set itself. Right? GANs does that. Has the ability to do that. This ability is not there before, not to the extent that we have now, okay, with GANs or convolution, after convolutional networks and GANs. Okay, previously data distribution, capturing the data distribution is a very tough task. The reason, as you know, as you can estimate, is given 500 samples, we are asking to generate, get the whole picture of it, right? So it is very difficult. That means from where these have come. Can I generate more of such things? Okay. So essentially what here interest is on maximizing the P of y, that is given P of y given the sample x. Okay. Here the interest is in capturing P of x itself. Given samples, from the given samples, can I get the distribution of samples? Or P of x comma y. Of course, y is also with me. I can get the samples and their labels as well. Okay. If I can generate more of one class means I know labels anyway. So R P of x given y. Okay, so here it focuses on x, here it focuses on y. Okay, so this is a much difficult and much complicated problem that GANs solve. So what that does is essentially, of course, before GANs. So how it is addressed in essentially learning setting or machine learning is through autoencoders, wherein we give some input features, set of features, and we want to see that same features can we get back at the output. And in between, you may have a feed, if it is feed forward neural network. Okay, you may have from 100 cross 1 to 5 cross 1, okay, or 50 cross 1, 20 cross 1, and then go back, okay, to 100 cross 1. But input to output has to be exactly matched. That is called autoencoder. Okay, if I can do that, what is the advantage? In a scenario where I probably I better input, okay, and there it is not mainly used for complete generating new scenario, but what is it used for? Is if I add noise here, okay, and then denoise one I can get here, okay. That means I can have a I can apply for better task. It looks similar to original, right? So once I learn that, I can do a kind of a denoise some of the aberrations much better, which looks like original. Also, these features can be effectively used as the encoded information of this. That means like we want to extract better features for doing many of the tasks, right? So these are all also used, can be used as features. And with that, some kind of base samples can also be generated. So this was the initial developments. After that, the GANs has made the problem slightly different, posed them slightly different. See, the idea here is, as I mentioned before, okay, the labels and input, okay, the input samples are not directly can be seen. That means, see here, the input is this we consider as input. Here we may give a random noise. Okay, random noise is essentially, if I have, the idea is, if I start from an arbitrary distribution, okay, so I initially start from uniform distribution, but my original samples of the data set are from Gaussian distribution. Can I just randomly generate several of uniform samples, which I can easily generate? Okay, and I want to capture the distribution of the samples which I have with me, which are Gaussian with n 1,5 or whatever. Can I capture it? That is the idea. The idea is, can I learn the distribution itself? Can I generate this generator? Can I learn the distribution from the base distribution, whatever I consider, to whatever I want? Okay? And this discriminator, what it does is, it has the ground truth samples or ground truth distribution parameters. It tries to check, okay, how good is that matching with this? Okay? So this is in this, there are two things to be done now. One thing is we have to learn the generator, okay, to generate better and better samples. But discriminator also should be learned, because this is also a model to be learned such that it can discriminate better. Okay, so but these are done in a player game, like a game. The reason is they pose it as a discriminator. Initially generator doesn't know anything, so it generates some fake or vague information, and that is directly given to the discriminator. Like we submit the papers and thesis to the supervisors. Okay, we write something and send them. Okay, and he also, of course, he's learned, but we want to learn it such that it discriminates. It says that it is fake. Okay, real is real. Okay, it distinguishes. And then says, give better information that, okay, you have generated wrong thing. Then it again learns. Okay, and again sends back. Also, couple of iterations. Okay, both learns. Okay, both gets their objectives. So essentially now if we put in terms of mathematics, what essentially we are trying to do is generator, if we see at the generator front, see G is the, so you can consider the whole network. I can represent it with G. Okay, G is a function. Okay, with parameters of generator. G of theta, for example, parameters here. And then D is the parameters, D is the, again, this network. Okay, D of means the whole function that the discriminator does. Okay, so now if you see here, D, so what output I get after at the output is essentially G of, okay, D of X. So for example, if I see X here, G of X I will get here. Okay, the output here is G of Z here. Sorry, G of Z I will get here. I will put it to here, so it will be D of G of Z. Okay, this I want to check whether it matches with the label or not. See here in cross entropy, what we do? Essentially, this we want to, if it matches means it is 1, otherwise 0, right? So minus log of that will be, if I minimize this, essentially I am maximizing the probability. That's all. So what I'm doing with the parameters of the generator, I want to maximize. Now I want to maximize the parameters or minimize this loss function. Okay? Maximize the probability or minimize this loss function. Now, this objective of discriminator is what? Say discriminator has two things in it. One is it also can see the real sample. Of course, it can see this information. It want to maximize that. This whatever probability of discriminator it want to maximize. That means given the input sample, it want to real sample, it want to maximize the probability. And generated value, what it want to do is, see, generated value it want to essentially see if it directly maximizes this d of g of g. See here, this it want to say that it is initially assume that it generates fake value. Okay, g of z is fake. Okay, it want to say that it is fake. Okay, and this it want to say that it is correct. So it want to say this is correct and this is fake. So to say that this is fake, 1 minus of this it want to say that it is correct. Okay, so to say that it is 1 minus of this is correct, we are this is the cost function essentially. And what this says is if I give real sample, it has to tell that it is real sample. Okay, so these are together, it maximizes or minimizes. Okay, so the last function it minimizes, or these properties it maximizes. It maximizes the property of real sample, saying that it is real through discriminator. Okay, it also minimizes the generated sample, saying that it is fake. Okay, so it does both together, right? So there are two things for the discriminator. It want to say since it is real and as well as the fake sample, it want to say that the real sample is okay with minimum loss. The generated sample is with maximum loss. It does that. And what happens? The generator now, gets adjusted saying that no, I'm not wrong. I will make myself correct. Okay. So these go parallelly. After some time, the discriminator will not be able to tell whether it is real sample or a fake sample. So it will settle at points. Okay, so they essentially, if we see in 0 to 1 scale, this will settle at points. So whereas this has to maximize, so it will go to 1. So that's the object. So essentially, this is done, of course, since we have two models to train, it can be trained first, generator can be trained, and then discriminator can be trained, and again goes to generator and discriminator. And then it does few iterations of generator and few iterations of the discriminator like that. So it's actually a kind of a train together, but in one after the other, and then training in few iterations of this versus few iterations, and goes in a iterative way. The whole thing goes in an iterative way. This is the overall cost function. People also write together so that both are mentioned here. As you can see here, see the first term is same as this term is this term and this term can be written together. Okay, so bringing that, what we want to do is we want to minimize with respect to generator. Okay, this is minimizing means 1 minus minimizing means maximize. Okay, and then we want to maximize with respect to the discriminator. Whole thing, and we have written such that the discriminator is maximized. And here the as you can see, we can start with random noise and random distribution. And what here we want to map is initially the experiments are to map with respect to uniform to Gaussian and so on. And later people were able to use efficiently using convolution operations, call it as deep convolutional GAN, DC GAN. So wherein they were able to generate good digits and good images as well. So and then the discriminator is like simply like it's almost similar to a convolutional classifier, convolutional neural network based classifier. Okay, this is convolutional neural network based classifier, and this is a generator. This is a new block, right? So this is also described in different ways. Okay, critic based approach and so on. So I skip the some of the GANs. The problem is they are like again like transformers. They are elephants. Okay, you can't train them easily, and they don't converge also. So there are several tricks people have played and then developed to converge the GANs. So in fact, those who start working on GANs will feel at the beginning that whether they converge or not. So now, of course, there may be some good tricks and already. They are also applied in different applications. Of course, you can visualize them better after a few iterations and so on, because here finally we are generating images. So initial results were little meager, but later now we can generate very good images through GANs. Of course, they are used in different applications, including some of them in medical. So there are several developments in GANs as well. So essentially, since they doesn't converge, which are the good cost functions they have explored. that is done versatile GAN, and conditional GAN and cyclic GAN I will discuss properly info GAN. Style GAN to people also see that since you have handled over generating the data sets. So if I may, how do I generate them differently? In the sense that say, instead of generating arbitrarily, the whole concept of all this conditional GAN, info GAN and style GAN, all these things are. So instead of generating randomly some say characters, say what usual GANs does is they generate 5 digits, mean 5, 8, something like that they will come. So one number from the digits because you line the whole distribution together. But can I generate whatever number I want? Okay. And when I want to generate faces, okay, I am generating with some kind of faces. Can I generate with specs, without spectacles? Okay, with height scales, with different variations. Can I do whatever finer variation I want? Okay, and generate that. We can do that by adjusting the logics essentially. So there are, once we generate and see pre-final layer, essentially in the discriminator, you can see that each of them will have different characteristics. If you add some noise or if you change them slightly differently, you can get different things generated. So they are explored, and then so you can do many things with GANs. So those who want to do mainly artistic stuff, okay, they play with GANs and like specs adding, removing. So you can play with features there and generate samples of that song. There are different variations. This is cyclic GAN, which is to generate from one object to another or one form to another. Say instead of distribution, raw distribution to images, can I one image distribution to another image distribution. So essentially here there are 2 GANs. Each one will generate from here to here, and whatever it generates, it will again use to generate again. And this is used to one discriminator checks this, one of the discriminator checks this, and it goes in a consistent manner. So of course they're also used in several other applications. To, for example, from labels to images, from to annotate, and to apply in other applications of computation. I will discuss briefly on flow of them. This is conditional GAN. As I mentioned, the conditional GAN, info GAN, and in style GAN also, they try to perform or generate objects of our interest or in a particular manner. Here is, see, if I want to generate only a particular character, say 8 I want to generate. What we give is, we give a label also. Some label in some kind of a encoded form to the input as well. So when we give the label also at the input in an encoded form, in some form, then it will know that we have to generate the label of A. That means we have to generate A. It has to generate A. So it can be trained in that way. So what we are optimizing here is X given Y. That means we are label is what we are giving in a supervised. These are all supervised methods only. So in a supervised manner, you are giving the label as well. Since you have it, we can give it and generate particular objects of interest. And this is info GAN. What it does is, see, instead of giving the label, the idea here is, if I want to change, say, rotate an object, generate object with different rotations, generate object with different scales, or a particular different variations. How do I do it? See, for each of the tasks I want to do, I can use some code vector, and that code vector I will give here is of a label. That means it is a kind of unsupervised here. Okay, so the code vector I generate, for example, if I want to generate, say, with height scale and without height scale. Okay, or with rotation, same object I want to rotate and generate. Okay, so and then I give one code vector. Code vector is also like a distribution. Okay, I give n 1, 1 for one task, n 2, 1 for another task, like that. And what we want to learn is, here we want to get output of the code vector as well. That means parameters of the code vector. This is also like an encoder. This is learned through Q learning. Those who are a little bit familiar with the reinforcement learning, or it is used through mutual information. So mutual information essentially is a kind of entropy based approach. So we want to optimize or maximize the mutual information as well with the code vector and generated images. And this also helps in disentangling the information and generating whatever information we need. So our student has worked on it for tracking. So we have put more information here. So you can generate particular objects and particular ways and so on. And this is applying GANs for computer vision. One of the examples I will give here. So essentially, if you want to do super resolution, we know how to make a super resolution network through convolution operations. Essentially, like segmentation we have done, right? So if you want to do better segmentation using GAN, okay, I think segmentation GAN is also there. So how do we do better? So we perform like a perform segmentation here. You give the labels of the segmentation here and then give it to the discriminator and see whether, of course, the segmented image or something, you try to see whether the labels are good or not. Essentially here is, we want to do super resolution. If the super resolved image is here already, we give the super resolved image here to the discriminator, of course, from here to here, we give it to the discriminator and give a original image also to the discriminator and say whether the super resolved image is as good as the super resolved image. In a conventional setting, what we do, we give the super resolved image here itself. Okay, in GAN-based framework, we assume that it is trained independently and it is trained first how to give the super resolved image here. We take the super resolved image from the generator. We assume that itself as a generator. Give the output of generator. Okay, and the ground truth as well here. Okay, both of them you try to check with this and try to see whether discriminator says good or bad. Okay, so this is a kind of fine tuning the conventional methods through considering them as generator and fine tuning through discriminator. So this is also used in object detection. Object detection, say here the problem is small objects if you want to detect. I know the features for bigger objects. I also have the features for smaller objects. Okay, can I apply, can I use them in a better way to say at the beginning I just make a kind of a feature extraction and these are given to the discriminator and say that the features of the bigger object I want to check whether they are similar to smaller object. Also, I have two different scales. I want to give it to discriminator and check whether they are same or different. Also, perceptual GAN does that. So there are several versions of them also for different computer vision tasks. So essentially, the idea is they does it like a generator is like a conventional CNN based architecture, and the output of the conventional architecture is given to the discriminator along with the real sample, and discriminator checks whether it is real or not. Also, it is also done in tracking. In tracking, our group has developed a method for GAN-based trackers. We initially have done like exactly as I mentioned, give a track from the conventional CNN-based tracker, and the real track we have and want to see whether through display. Subsequently, we have developed a method with InfoGAN-based approach, wherein the code vector also is given, and we want to predict the code vector. The prediction, whenever it goes wrong, it means that the tracker might have lost. So we would like to see that if the tracker is tracking well or not, can it be obtained or identified through code vector. So this is not there in conventional trackers, because conventional trackers, if they are able to track, they will track. Otherwise, we miss the track. So this also gives a quantification of how well we are tracking. That also helps in terms of tracking vector. So it's the details, and these are the details on the scans. So probably what I will do is I will quickly go through few other slides of our group, where probably in 5 minutes I will wind it up to give a pointer to what our students are doing, and probably of course some of them I have discussed already, but this is just to give other aspects of it. So IIT Tirupati is now almost full-fledged with whole campus and quarters there, 100 plus faculty, and then 1500 plus students, all staying in the all operations from the institute. You can see those whoever are here can visit. It's a nice place to visit, both in natural scenes, both with natural scenes and then other things. This is our department. 4 departments are housed in this departmental building. We have 2 departmental buildings now, with almost very good number of labs. We have a computer vision and image processing lab. Of course, we named it as VISA lab. So visual signal analysis and learning lab. 2 of us are faculty in that. He works in Dr. Subramaniam Gorthi. Hopefully, he will also be giving a talk. He works in medical imaging. This is our lab web page where you can see the students there and then different publications and so on. We have the MS, MTech and PhD programs at the institute. MTech in signal processing and communication is there. Of course, MTech in computer science are also there. MTech in computer science and signal processing and communication may be relevant. We work on different areas of computer vision, deep learning, machine learning, and so on. We have very good infrastructure. In fact, I think it's one of the institute which has a large number of GPU computing facility. So we have 30 GPUs with 4 GPU cards of NVIDIA RTX 2080, and we have close to DZX kind of machine, which has like a DZX A100. Those who are familiar, which has 640 GB GPU processing. So those who really want something also can write to us in case there is a provision we can explore. We could probably give the opportunity. Those who are want to work physically also are welcome for either for internships or for your higher studies. We do have other gadgets on these for different computer vision experiments and operations. So of course, our students has usually participate. Visual object tracking challenge is one which I have been participating or which I have been exploring, and many of our students have done very well in terms of being part of our selected challenge. And so many students got INEA award, student INEA awards. And in some challenges of the workshops and then conferences also people have got. So we publish in different forums, including transcriptions and then good journals and conferences. And of course, the students, Chandrasekhar itself, he himself has prepared the slides. So he has put some slides in students list as well. So these are all the early students of MS passed out. Some are there in CE, he is now at GE and it's Qualcomm, and both are in startups. So the PhD students almost done. So with final, Chandrasekhar anyway is connected. So some of the other benefits. There are a large number of MTech students graduated. Good number of others. So of course I will not give full details or more details. One of the other area which is not conventional computer vision and where we work more is on 3D reconstruction from fringe projection. So we project some fringes on the object from the projector, and from the fringes we want to extract the captured fringes. We want to extract the depth information of the object. So ours is the pioneering group to come up with a deep learning based architecture for this application. In fact, it's the first one with more than I think 150 citations. And then subsequently several methods have been developed in similar lines. And then how to come up with a phase and tracking method. Say there it requires phase and tracking, how to come up with a phase and tracking there, or from the fringes directly. So apply it on so different kind of fringes. So if usually the sinusoidal fringes has some disadvantage, linear fringes has some difficulty. If there is a depth more than 2 pi, okay, it looks like exactly without depth. So exactly 2 pi, it looks like without depth. So there are some problems associated with that, and we came up with some other kind of fringes which will help to do that. So these are few other areas. Of course, these are few other areas. So imaging flow cytometry is other area where in medical image applications, where it is not, the blood cells are imaged without stain. So usually if in microscopic slides, we add the stain first, and then the color, white blood cells, red blood cells, all will be visible differently. If we don't add stain, there is a microfluidic channel. If we make them to flow directly, so this is there is a flow of cells here. I don't know whether you can see. Those you can. Here challenge is we can't. We don't have features. So better feature extraction, better pre-processing, all that need to be done. And from here itself, if we can classify, then we can do billions of cells. Usually in microscopic slides, if you want to do, we can only do each cell has to be done separately. Here, we can flow each small blood sample has millions of cells. So you can do it very large scale. This is together with IASC, where my brother is there. So instrumentation and graphics. So he makes the instruments for biomedical applications. He's expert in the field. And this is satellite image processing segmentation. I was previously at IAST, Indian Institute of Space Science and Technology. By nature, our institute and in collaboration with ISRO, were exploring about the applications of satellite images, finding the motion of clouds, some such applications. We will have works and publications on these. And these are a few of the use cases of current deep networks. So in terms of crowd counting, it does count reasonably well. So that's all. Yeah, thank you. And if you have any questions, you can. Yeah.
What is the evolution for these GANs?
Can you tell them what is the
Evaluation metric.
GANs? Oh, usually they use cross entropy only. Discriminator uses cross entropy. Even generator also uses cross entropy. Because, of course,
That's a cost function, but evaluation metric.
Evaluation metric. You want to see whether how good are they generate. Okay. Okay. So if you essentially by visual, mostly it is done through visual comparison. But quality assessment methods are there parallel to see whether they are good or not. Hopefully, I'm not very sure exactly on what whether they are used here or not. But NIQE mean opinion score. The mean opinion score is essentially if we ask 10 people, each of them gives some opinion out of 1 out of 10, right? So mean of that is mean opinion score. So a neural network model for it is essentially NIQE is a neural network model. Similarly, there are other models. So which are learned on with the feedback with data of many people and so on. So those are usually used for quality assessment. NEMA score also is used, but in this context, I'm not very sure.
And in one account of training of this, what I understood is that first there is a generator which takes the input of the noise and generates one sample image. And that sample image is fed into a discriminator, which discriminates to take or take from it. And also, along with the generated image, the real image is also fed into this discriminator. And after this one, the cross function is calculated for both discriminator and generator. Generator managed to manage the distribution of the real data.
Correct.
Like training data. Like how the back propagation will work. Is it parallelly?
No, usually say discriminate, assume that you have the whole cost function, you make a full pass. Okay, and then you have the cost function with the D of and G of. That means generator parameters and discriminator parameters are involved in whole cost function. So what we do is we adjust the parameters of the generator. Assume that. Okay, and after that we make another pass. See how many times we adjust that depends upon different way of learning. But once we adjust, assume that now let's go back to the discriminator, and then we adjust the parameters of the discriminator. It becomes slightly better, right? So and then come back to the generator. Okay, usually people do some iterations of this plus some iterations of this.
I mean, the generator it will be a chance conversation where you're going from small to big.
Yeah, correct.
In that batch propagation, will it be like downsampling, like what you have said in the it's the same logic.
Yeah, correct. Batch propagation procedure is same.
And one thing
And of course, they apply several tricks on, say, for example, like two cost functions are there, right? So, like one only if you spend more time versus, okay, and then first optimize one to some extent. How much times one has to be optimized across other? Such things are explored.
Because a greater discriminator should not be used when less generator.
Yes, correct.
One thing you said about the perceptual gain, use in object based. How it is used.
It's how is it used means you want to know how it works or how well it does. It is used essentially for a small object detection, wherein you want to detect smaller objects. So essentially, it does super resolution within it. So it is doing the super resolution of features.
Like what you said is one main application is that to find the small objects while doing the object test.
Correct.
And is it useful for the on-stage object detector like yoga also?
Oh, fine. This doesn't come in one stage. Okay, you are saying if I start with an object detection model and then apply perceptual GAN does at the feature level, super resolution and match it. See exactly this. So it trying to generate the features, okay, of smaller objects, okay, which doesn't see if I have a deeper architecture, these features will be like this only. Okay, I send this similar bigger object also assume that I have. Okay, and these are not same, not necessarily same, but I know that features of this has to be similar to this because the objects are same. Okay, so I give these features and this feature, these two discriminator and say that these two should be same. Okay, like this I try. This is perceptual. This model is slightly different, wherein I use the complete architecture. So if I have already super resolved some CNN architecture for super resolution, I directly borrow that. Okay, SR GAN, for example, super resolution GAN. Already there is super resolution architecture. Okay, that takes directly. Okay, and gets an output from trained model. And that model is given to this, and then ground truth is given, and then we check. And then fine tune both of them. Fine tune this also. Fine tune both of them. Yeah.
Okay. So thank you very much, sir, for your wonderful talk. So the way the students are interacting with you, I think that your talk was very awesome. So they are taking a lot of interest. Of course, like if they have any doubts or anything, so they would try to communicate with you.
Sure.
And once again, sir, thank you very much. So early morning you wake up and physically you come here. So that is really the inspiration for like such a young researcher or faculty for us. So when I see you like continuously you have been teaching for the 3 hours, like it's not a cup of tea for us now, but you are really, sir, you are inspiration for us. Thank you very much, sir.
Thank you.